Hello everyone, my name is Junjie Wang. I am a CS Master Program student in National Taiwan Ocean University. Today I will present the topic of PTM puzzle tile map, a novel method for visualizing spatial-temporal data. Before introducing today's topic puzzle tile map, I will first introduce what a tile map is. Tile maps are an important tool in semantic cartography with distinct characteristics from the well-known tools such as choropleth, cartogram, and symbol maps. The tiles in a tiles map placed in a grid at a position that approximate their geography position such that each tile has identical shape and size. Tile maps provide an easy way to visualize how a measurement varies across a geography area, and how the level of variability within a region. There are many time series data in our daily life, which is generally visualized by diagrams such as line chart and heat map. Most of this time series data contains geography information, which is referred to as spatial-temporal data. This kind of information can be seen everywhere in our lives, and the data need to have three basic dimensions, namely data time, geography location, and data value. And this is our puzzle tile map result. We can see tile map with puzzle pieces and showing spatial-temporal data in a static 2D diagram. The following is related work. The profile of single time series is represented by a data vase and plot along a vertical temporal axis with time increasing from bottom to top. However, there are limitations of temporal information visualization. When the data contains geography information, the 2D static methods are difficult to display the geographical relation and distribution. 2D visualization methods have more space to display spatial temporal data, but the disadvantage is that the data value will overlap. The following research is related to tile map. The first one is to generate a tile map by calculating the relative relationship between the administrative region. The next article is to improve the layout through the simulated annealing algorithm and put a simple bar graph. And this one is to generate a plain tile map and then match the administrative region. We study the advantage and disadvantage of related paper to generate puzzle tile map. This is the flowchart for generating puzzle tile map. The upper part of the chart is the process that can input this continuous map data to generating a map. The lower part is to input the data that need to be visualized to generate a puzzle. We can combine the above two steps to get the final result. The upper half of the process of generating a tile map can be divided into 4 steps. The first step is to pre-process the map data, and then use the mosaic filter to get the tile map. Correct the position of the tile map, and finally optimize the administrative district pairing to generating the map. The first step is to simplify the input geography data and separating into several connected regions. A region growing strategy is adapted to check the connectivity of districts. In the picture, the 4 tiles on the left will be divided into one region. Similarly, the 3 tiles on the right will be regarded as the same region. Before mosaicing, the map image is transferred to a binary image. The length regions are set to black while the others are set to white. Then the mosaic filters is applied to the binary image to generate initial tiles of the same size with the filter. In the tiles, if the number of black pixels is more than that of white pixel, then this tile is set to black and vice versa. The initial tiles generating using mosaic filter link can force the layout to be as similar as possible to the original geography map. Although the mosaic filtering allows generating tiles with a shape that fit well with the original geography map, the tile position may not match well with that of district in the mapping process because of the inconsistent area between tiles and district. Take the example in the picture. New York is placed in the middle position, but this is not what we expect. To evaluate this problem, we define the boundaries of the input map based on the density of district. In other words, the map region containing dense district will be enlarged while the region containing sparse district will be shrunk. Then, define the boundaries of the geography map to generating a tile map. Taking the example just now, we will get an enlarged map of the east coast of the United States. Therefore, New York will also be assigned to a relatively correct place. The generated tile map may encounter the following two problems. The first one is mosaical filtering is performed with the shape of the map. However, the method does not consider the case of multiple connected regions. And the second one is to generate the desired number of tiles. The initial tiles for each connected region are generally generated with a mesh with different grid size depending on the region of filter size. To make sure all tiles have correct connection, first order neighborhood is used to define as a continuous area, and the others are defined as non-continuous area. If a tile belongs to a region without first order neighborhood, the position of that tile is rearranged to the nearest vacancy that connected with that region. For the second question, we propose an iterative method to correct the correct relative position as much as possible, while also reducing the layout. First, we initial tile map and shift to approximately proper position, and shift outside, and check overlap. If there is still overlapping, then shift outside again. Given n district and n tiles, the problem to be addressed is how to search for the optimal one-to-one mapping between the district and tiles. The goal of This mapping is to minimize the distance between the tiles' position and their corresponding geography position. Specifically, the defined object function considers not only the position, but the orientations of district, and thus, an appropriate one-to-one mapping between the city and the corresponding tiles can be obtained. This bipart tile problem is solved by using the Euclidean algorithm, which provides an efficient way to find the optimal solution. In order to visualize time series data on tiles map, an aesthetic pattern, that is puzzle, is adapted to represent time varying data. A puzzle pattern consists of 4 characteristics, including district name, puzzle pieces, puzzle connection point, and event point. According to the research of Gustav Physiology, there are about 5 to 9 elements that humans can recognize. We took an average of 7 colors to represent different data intervals. However, a suitable number of color classes may lead to a problem that it is difficult to display the variation between adjacent pieces. In this study, this problem is addressed with the piece connection pattern. If the data quantity in the current piece is greater than that in the previous piece, the piece connection pattern will be located more closely to the inner boundary. The locations of the piece connection patterns allows users to observe the change rate of data quantities between 2 adjacent puzzle pieces. The first example is air pollution data in Taiwan 2016. The data contains air pollution quantities of each city in Taiwan every month. A dark color means a bad air pollution. In this case, the seasonal and regional air quantities can be observed from the puzzle tile map. The air quantity in summer is better than that in winter in many cities such as TYC and GNN. Apart from this, the air quantity in central and southern Taiwan is worse than other regions in Taiwan. The second example is the transfer of residential property in Taiwan from the fourth quarter of 2013 to the third quarter of 2016. In this example, the red point means an event that the government revised a real estate taxation regulation, that is, consolidate house and land tax, which took effect from the first quarter of 2015. This regulation encouraged people buying houses for self-use rather than investment purpose, which brings some negative consequences on the real estate market. The puzzle tile map is a novel visualization technique that combines various characteristics into 2D space without sacrificing one of the characteristics of spatial-temporal data. The proper spatial-temporal visualization represented by 2D diagram can focus on time series data in a specific region from the geography perspective. Our method has the following limitations. The proper method is not a sustainable visualization to gain significant details from the large volume of time series data. In the future, we plan to expand our method to make the puzzle tile map run on various devices with different screen size. A hierarchical visualization strategy with different levels and numbers of tiles is a possible solution. Thank you for listening.